Live.
Going live. All right. Welcome, everybody, if you're an early bird.
Wait, it still needs to load.
Okay.
There we are.
Okay.
Right.
Hallelujah. We are live from Curiosity Peak. This is Doug and Vivek here.
Hello.
And we've got some neat objects we're going to look at tonight. Just want to mention that tomorrow is a special day as we zip around the sun. Summer solstice, which means that we're, got a ways to go to get to the other side. It's going to be the longest day of the year and the shortest night of the year. Of course, we astronomers like long nights, but we don't like the cold too much either, so we're cool with that.
So we're just going to wait for like maybe 18 minutes and then we'll get started with the rest of the
Yeah, we want it to be completely dark.
Yep.
And we want to say happy birthday to Jerry Hilburn. And happy Juneteenth, too. You know, we know there's people who want to hear that. And we're cool with it. So we have a list of objects tonight we're going to look at. We're not even going to mess around the solar system. We're going way beyond, out into the Milky Way and even beyond that. So we've got some galaxies that we're going to look at. We're going to see how galaxies behave when they get near each other. And they do some pretty interesting things.
Yeah.
We're going to look at planetary nebulae. And what are planetary nebulae? Having to do with planets? Nope, not a thing. But they are the ghosts of dying stars. And they're very interesting, very beautiful. So we're going to do that, and we're going to swing by and see a globular cluster too, one of the largest one that you can see in the northern hemisphere, which I think is like 500,000 stars.
Yeah. So 300,000.
300,000. Okay. And also, we want to encourage people to chat with us and send in comments and questions, declarations, anything that's relevant.
We got Comet C2017 Pan-STARRS T2.
Ooh, I told a big lie. I said we weren't going to mess around the solar system.
Yeah, well, we're right here in with the solar system.
Okay, we're falling back to the solar system. Okay. We know that, it's this pretty small place, but we like to explore it. And this is a comet that is in sight right now. So Vivek is kind of fine-tuning the equipment to get us the best view we can get of the comet.
Yeah. Well, we got a galaxy.
Oh, there's a galaxy down there.
Just a random galaxy there, yeah.
Talk about perspective. Yeah, so we got an object in the screen that's in the solar system and one that's way beyond the Milky Way.
Yeah. There we go. Now
okay, yeah, it looks kind of green now.
We should turn off the red.
Hmm?
Turn off the red on the color balance.
Okay.
That's a little more. Yeah, I think we can go with the bigger black point. There
so
we
where
are.
am I going to see the chat? I'm looking for that oh, right there. Okay.
Yeah. Oh, we got a good color balance now.
Okay.
You can see the green of the comet. That's because there's carbon on the comet that's emitting light in the green and blue parts of the spectrum, so we get to see that out of the comet. So
is that comet on its way toward the sun, or is it
going away?
Going away, okay.
Yeah.
All right. And that little fuzzy item down there toward the bottom of the screen.
That's a galaxy.
That's a galaxy. We don't know which galaxy it is, I guess.
Well, let me see if we can. NGC 4085.
Oh, okay.
So let's see.
That ring a bell?
That's 78 million light years away.
78 million light years away.
Yeah, the comet is C2017 Pan-STARRS T2. You can see it right here on Stellarium. I can click on the comet. That's the name of the comet.
Yeah, so that's just a little added something tonight. We've got a comet on board.
Yeah. Well, we'll let people file in.
Oh,
that's 6
Fred,
viewers.
Name of comet. Fred wants to know
Yeah.
What's the name of the comet?
Well, yeah, I just announced that. Yeah.
Oh, Pan-STARRS?
Yeah. See 2017. It's discovered in 2017.
Okay.
And based on this, there was a lot of comets discovered in this month, because this helps you designate like the second comet in its month.
Mm-hmm.
So.
Now,
Yeah.
hasn't there been other comets named Pan-STARRS?
Yeah, Pan-STARRS is a survey in Hawaii that's dedicated to finding near-Earth objects, asteroids, and comets. So they're really proficient at finding comets because that's what they do. So a lot of them are going to be named after Pan-STARRS.
Mm-hmm.
A lot of them are named after the Catalina Sky Survey that's in Arizona atop Mount Lemmon. There's also the Lincoln Laboratory, but they use a facility in New Mexico. I forgot what it's called, but yeah, there's a lot of different.
Minimize the screen, which makes it hard to read for all eyes. Oh, that's the Pan-STARRS, yeah. Can you hear us all right?
Yeah, it's just a little hard to change what the name is. Yeah, let me turn this up. There we go. That's a better stretch. White balance, increase it. Oh, that's a little too much. Okay, there we go.
Yeah, so the tail kind of extends down, doesn't it?
Yeah.
Looks like.
Well, you can see. Yeah.
Mm-hmm.
It's interesting behavior.
Yeah.
Well, I wonder if we can do longer exposure on it. Maybe do 20 seconds. We'll have to turn on the gain a little bit, but see what that gives us.
Okay. Anybody have questions about comets? We sound two football commentators.
Yeah.
Hi, Terry. Okay. Sorry about that. Well, gee, we'll get more serious, I guess. Or
Yeah, we're just waiting for people to come in. The event really starts at like 9:15.
Yeah, that's when astronomical darkness really occurs. The sun has to be 18 degrees below the horizon before we call it dark.
Yeah. Let's get the stretch better.
So what constellation is it in?
Right now it's in Ursa Major.
Ursa Major, the Big Bear.
Well, let's look at the entire context.
And you could probably catch that with binoculars, couldn't you?
Yeah, in dark enough skies.
Okay, well, what do you think? Should we move on?
We still have 11 minutes. I mean, it's getting dark, but it's not quite dark.
Fred wants to know what the official time was for the image. We
9
said
o'clock.
9 o'clock to 10, starting at 9, which it's already 9:05, and we're going till 10:30. And Tijuana is socked in. Oh man, sorry about that.
Marine layer.
Yeah.
Brutal.
Really? You can understand us, Lynn. Okay.
All right, let's turn up this blue. Doesn't seem like it's getting enough of it.
So did everybody get to see the galaxy down there too? Only 78 million light years further away.
Let's get some people to zoom in on the comet.
Okay.
There's a comet. We got this nice little galaxy down here. It's a little bit too blue, but we got this nice little galaxy down here, and then we have a comet. So that should be a little better resolution for the stream. Yeah. Okay. Yeah. That's okay. There we go.
Yeah.
It's a little bit windy, so we'll have to wait.
Oh, Megan wants to know. Oh, she says we're doing all right. And Woody Schlom, hey, Tijuana being socked in is good. That's true. And San Diego is socked in too. We saw that. So we just want to extend our thanks to that marine layer that so generously blanketed the light pollution that we hate. And so we're going to have pretty dark sky. That'll help us. We're doing some imaging of our own, but
in the background,
yeah. But this will make our images that we're showing you even better. So,
what is the fuzzy planet in the middle of the left screen? That is a comet. That's Comet 2017 T2 Pan-STARRS. So,
yeah.
And we're gonna stay on it until like 9:15. So, while people join in, and then we'll go to the rest of the objects.
Yeah, we're gonna head out from the solar system though. Yeah. So you're going to kind of tighten your seatbelts for that.
Yeah, we have the images just filing in here, and we have where the telescope is pointed on Stellarium. It's connected to Stellarium, so.
Yeah, you can kind of see the constellation where it is.
There it is, yeah.
Yeah.
And it's still getting dark, but
you want to run outside with your binoculars if you're in a dark place, and
it's still going to be there tomorrow.
Okay. Yeah, okay. But it is moving out of the solar system.
Correct, yeah.
Or at least out of our part of the solar system. Yeah, okay.
Us TJ astronomers are considering blacklisting. Okay, yeah.
Okay.
Oh.
All right. So good question, Lynn. Fuzzy things can be comets, or they can be nebulae or galaxies, and
yeah,
we're fortunate enough to have equipment that we can get close enough to see. But back in the 1700s, when people were starting to catalog the sky, it was hard to figure out what things like that were.
Yeah.
But that's when people started hunting comets. Halley, for example.
Yeah.
Okay, there's Roy. Hey, Roy. Good to hear you.
Yeah. Okay. We're getting close to that time.
Yeah. Okay, so 9:08.
Yeah.
Okay.
We have a pretty okay view of the comet.
Mm-hmm. Well, this comet didn't disappoint. Some of them do. Lynn wants to know, what is the string of bright objects below the comet?
Those are stars, and one of them is a galaxy.
Yeah, those are stars. They're in the Milky Way, so they're in the same, in the same neighborhood as our solar system. But the comet is in our solar system. Most comets fly out of the, the Oort cloud?
Well, some will come from the Kuiper belt, some come from the Oort cloud. So,
which is the outermost part of the solar system.
Yeah.
And they're balls of ice and rocks and dirt.
Let's zoom in on the comet again so people can see a better view of it. So yeah, that's the comet over there.
Yeah, Lynn, keep firing the questions.
Then we've got one really nice galaxy here, and you see, what was it again?
Yeah, see, that's another fuzzy down there.
There's a lot of fuzzies. There's a cluster around here. Yeah, this is NGC 4085 down here. Yeah. Yeah.
Oh, I can see what you're doing on the screen over here.
Yeah. I don't think the latency is okay. Yeah. It's not a huge latency.
Okay.
Okay.
Well, shall we move on? What do you think?
Yeah.
It's 9:10.
I think we have people tuned in, so
yeah,
let's go on to M109.
Okay, M109, Galaxy time.
All right, here we go. Let me punch it in.
Okay, now hang on because we're moving.
All right. That wasn't very far with the telescope. Okay, let's decrease exposure time. It's going to be just trails.
Well, trails are okay. People know we're moving.
Yeah. Let's turn up the gain all the way up.
Okay.
2.5 seconds. Yeah, that's a bit too much. There we are.
All right.
It's a little grainy. You can see it. Let's turn down the gain. Let's increase exposure time.
Yeah. One thing for people who don't do amateur astronomy, which I don't know how many of you are out there, but taking images of things in the night sky is a little tricky because they're faint, and you need to get a lot of photons before you start to see them. So when we do imaging, serious imaging that we're going to save the images, we do it for minutes at a time, and we do multiple images and stack them together and process them to bring out the details and the fainter details.
Well, there's the M109.
So this will give you an idea because this is a galaxy.
We can't quite see the spiral arms yet. We need to take a longer exposure.
Well, I can see them now, kind of.
Yeah, but let's turn it to 10 seconds.
Okay, we're going to do a 10-second exposure, so we're pushing it.
We can do 30 seconds
Yeah.
when we get... Okay, that's getting better,
Okay.
but I'd like more.
I don't think we can't stack on the fly, can
I mean, taking exposure, longer exposure is stacking on the
we?
fly.
Yeah, okay. Yeah.
It just takes a little long to
Okay,
load
so-
the image.
So how long is this one going to be?
30 seconds.
Okay.
All right.
So you'll see the difference it makes from a 10-second exposure to a 30-second exposure.
Okay, it's getting better.
Oh, so, okay, we're getting linked to the Julian Connection Facebook. Thank you, Chip. Okay, Fred wants to see two tails.
Right,
What did you do with the other tail? Okay.
That's this is too long. Let's do 30 seconds.
Well, sorry, Fred, we're on to the Galaxy.
See what we can get out of this galaxy. Yeah, so M109 is a barred spiral galaxy, and so it's kind of similar to the Milky Way, and so it's a really good analog. So what we're going to do with the rest of the objects is show you how different galaxies can be, especially when they start interacting. So this is just a lone, very normal barred spiral
there we
galaxy.
go.
Yeah, there we go. That's pretty good.
Yeah, okay. Well, that gives you an idea of the structure of the galaxy.
Yeah, let me zoom a little bit out.
And galaxies don't all look the same. There's just an incredible
Range.
of galaxies, and it's quite common for galaxies to come close to each other, close enough that they start interacting. So this one's alone out there, right? It's not, doesn't look like it's getting mauled by another galaxy.
Yeah. It's doing okay by itself.
Well, we got a wow from Lynn. Okay.
Let's turn. Now we're just pushing the image to its limits.
Okay.
But yeah, that's a good view of that.
Do we
galaxy.
need those crosshairs or?
Well, we can turn them off.
Yeah.
There we are. Okay.
Yeah. Okay. So that's M109. What constellation is it in?
We're still in Ursa Major.
Ursa Major. Okay.
Let's
Ursa
look at
Major's got a lot of galaxies.
There we are.
Yeah.
Vacuum cleaner galaxy. That's what Julian calls it.
Yeah.
It's right near the bright star Phecda,
Mhm.
which is one of the stars in the Dipper.
Mm-hmm. Yeah. One of the things I mentioned is when you want to look at galaxies, you have to do it when the Milky Way is not.
You want it to be low on the horizon.
Yeah, because the Milky Way is our galaxy, and it's so full of stars that it kind of in dust as well that it obscures or hides the galaxies that are, in that direction. So we are best able to see galaxies when we're looking outward from the Milky Way, not along the plane of the Milky Way where it's the most dense.
I forgot to turn the cooler on, so we might get this cleaner image soon.
Oh, okay, yeah. What are all those red and green dots?
Yeah, that's gonna go.
Interesting.
We're gonna get a cleaner image soon.
Okay, those are called hot pixels.
Yeah, temp. This is typical with the uncooled camera. So now we're gonna cool it down to get it.
We're plugged in to cool the camera?
Yeah.
Oh,
it's cooling. 9%. We're
Okay.
going down.
Yeah. The
Let me
cooler the camera, then the hot pixels start to relax and fade.
Yeah.
Because that camera sensor it's working hard.
It's doing its job.
Yeah.
Let's reset that again.
Yeah. Look at all the colors, right? Yeah.
That is.
Yeah. Well, those are not really part. They're not out in space. They're in the camera chip. But you can see a little color in the galaxy, I think. Anyway, we will be seeing some color.
Don't you worry about that.
Oh, we got Jeannie Anderson. Hey, Jeannie. Cool.
Let's wait for it. Yeah. I might have. Okay, we're below 0 degrees Celsius now.
Okay, we're getting cold. We like cold cameras. Warm nights and cold cameras.
Yep.
Yeah. By the way, we're not actually in the observatory. We're sitting outside. We've got Vivek's 12-inch Dobsonian scope, which is pulling in the light. And we got a new camera, a ASI 294 color camera, which enables us to
I
get
think we
color
have
images.
some high clouds over on 109.
Yeah, it's not.
It's kind of faded out.
Perfect, but, yeah.
Well,
Okay.
let me decrease exposure time so we can get a more live the image. Okay, there we are. Looks better. It's a little bit too much gain.
Oh, Fred. Man, he's a mean guy. That's what he says. I'm holding models, yeah.
Thanks for the appreciation.
Yeah, but it was a lot of work to build those little models, you know, make them look like galaxies.
They made our paper mache.
Yeah. And they glow in the dark, too. How about that?
Yeah, it's getting much cleaner now. Let me go for a longer exposure.
Okay. We're going to try to give you a best image possible on the fly here of the galaxy.
It's a bit too red. Let's turn that down. A slight notch.
And there's Ernie. Hey, Ernie. Welcome aboard. Now, this is a big reunion here.
That's 15-second exposure.
Uh-huh.
Here we go. 9.
Okay, 15-second exposure.
Yeah, now we're improvising in terms of getting the good picture. It's a lot of tweaking.
Mm-hmm.
Ah, there we go. That looks
Yeah,
nice.
Okay. Yeah. So if that was the Milky Way, we'd be in one of those spiral arms.
Yeah. I think the brightness might be too. Yeah, this is getting tricky. It's getting cooling down, so all.
Okay. Well, shall we? Let's see. It's. Shall we head on? Do you think to the Siamese Twins?
Let's just wait a little bit. We're looking at M109, which is a barred spiral galaxy.
It's one of the galaxies or objects discovered by Charles Messier, who was in the 19th century.
Yeah.
Or 18th century, I think. He made a list of 110 objects that he saw in the sky that were not comets, because he was looking for comets, so he wanted to figure out what are those fuzzy things up there that look like comets, but they really aren't. And the reason he knew they weren't comets is because they didn't move.
Yeah, the picture's much better now.
Oh, yeah. Okay.
Getting more of that barred spiral.
Mm-hmm. Yeah. It's a little smoother, too. Yeah.
We're just going to keep working on that. We're going to go to Siamese Twins soon.
Yeah.
But
okay.
Let's keep working on this.
So next stop is going to be the Siamese Twins.
Okay, there we go.
Which, not a very, cool name in a way, but we could call them the conjoined twins.
Let's do one last 30-second exposure.
Okay. Vivek's going to do a final shot here to give us the best possible view.
Yeah, false scale is fine, but why not tweak? We can see get the best out of the galaxy. Let's see, 12. Let's get.
Fred says it doesn't have to be picture perfect.
Indeed.
Just so we can see the major features. False color is fine. Okay.
Okay, that's good.
Yeah.
That's what we're looking for.
Okay. Yeah. Wow. That's pretty good.
There we go. Yeah, you can see the barred spiral really clearly.
Okay.
Yeah. The equipment is it's a 12-inch go-to dog. It's my 12-inch go-to dog with Doug's new ASI 294 MC cooled camera. So we're using the pair together to do some short exposures of objects. So.
And it tracks, as you can see.
Yeah, it does track. Indeed.
It stays on the target, so it's pretty nice.
Yeah, we got a nice image of M109 right now.
Mm-hmm.
I think we're ready to move on.
Okay, Fred want to know if that's an elliptical up in the upper right.
Yes, we can look at. Let's look at what the object. can see that the reticle, this orange reticle, shows where the Dobsonian is pointing. So that galaxy. Okay, it doesn't show any, but yeah, there's always going to be a lot of galaxies in the vicinity.
Oh, we got a moth flying.
Yeah, we got a mount.
Yeah, okay. Yes, we're out here with the critters. Okay.
Yeah. Okay. Let's go. Let's move on.
Let's move on. Okay. All right. NGC 4567.
Yeah. Now that's a good use. I want to like. Well, we're gonna use that too. Slew of the.
Okay.
So what is it?
Okay. It's 4567. Vivek just stepped into the cockpit. He's gonna move us on.
Let's go. Here we go.
So where's Jerry? I don't see Jerry there. Maybe he's just lying low. Streaking.
Yeah, you're gonna get a lot of streaks when you do this. All right, let's see if we landed on our target. It's almost there.
Okay, I see something down there at the bottom.
All right, let's let me get it to center.
Okay.
Right.
Okay, we're gonna get a little more into the screen. Okay.
There it is.
Yeah. Not one, but two. But it has one NGC designation. Yeah. Okay. Now you've probably seen a couple little fuzzy things there.
Yeah, let's do
close to each other.
Let's do a longer exposure on this.
Okay. Yeah.
7.5.
Now this is what you're seeing now is our galaxy will end up doing with Andromeda eventually, getting too close for comfort.
Yeah, there we are. The Siamese Twins.
Mm-hmm.
We got two spiral galaxies right next to each other, and they're on a collision course with each other. So they're right now, a lot of their matter that's outside the galaxy, we can see them interacting. That's how we know these are definitely two galaxies that are on a collision course. So in give it a few billion years, you're gonna have a lot of lots of spiral arms being thrown out, lots of stars being thrown out, and they're gonna condense probably into an elliptical galaxy. So let's see if we can get some more out of this image.
Yeah, and that stimulates star formation.
Yeah. Let's zoom in on this galaxy. It's a bit small, so 200%. There we go.
Yeah, now do you know the distance to those galaxies?
Let's look at it.
Okay.
Let's
there
see.
we go. We got the
let's see where we're pointing out. Okay, we're right now in Virgo. We're the middle of the Virgo cluster.
Mm-hmm.
There's a lot of other galaxies.
Yeah, look at that.
Let's see. Yeah, so these are Siamese Twins. Fish and chips, okay. These are 105 million light years away.
Okay, pretty distant.
Yeah.
A lot farther than Andromeda.
For sure, yeah.
Yeah, that's why they're small, because they're not too near.
Yeah. So, we got... Yeah, so...
So their gravitational force is wreaking havoc on each other and creating new things.
Let's up the exposure time.
Okay, we're going to see if we can get a little crisper image.
Yeah, there we go. It's a very strong image. Yeah, there's a lot of galaxies in this place. It's Virgo supercluster after all. Yeah.
Well,
It's
we're
right
part of it.
Right at the point where, like, if you have the entire Milky Way as a circle, it's at that nodal point where you can see into deep space very clearly, and you got all those different galaxies.
Yeah. How many galaxies in the?
Yeah.
Okay. Oh, Lynn
How
asked, close are the Siamese twins?
They are 105 million light years away. They're not very close. They're very far.
So they're farther than that other galaxy. That much farther.
They're like 210 times farther than the Andromeda Galaxy.
Yeah. Yeah. Andromeda's about 2 million.
Yeah. That's.
So it's pretty cool that we can see them, even though they're much farther away.
Yeah. All right.
Okay. So gonna go to M51.
Yep. Let's do it.
Okay. Any no more questions about?
Is anyone any more questions about these pair of interacting galaxies? Is this part of the
she wanted
filament?
to know how close they are to each other.
Oh, well, let's just say they're right now touching. They're interacting right now.
Okay.
They're actually, there's evidence of interaction between them right now. So they're in the process right now. They're colliding with each other.
Yeah.
Is this the part of the filamentary makeup of the local group? Yes. Yes, it's part of the Virgo supercluster. So, and it's part of the Virgo supercluster. Within that, there's a local group. So it's within that realm.
Yeah, we're the local group. We're
in the local group, and the local group is in the Virgo supercluster.
Right, and then our local group includes Andromeda,
M33,
M101, or
yeah, I'm not sure.
Okay.
I mean, M101 seems pretty close enough.
M82, right? And
yeah.
Yeah.
We got a lot of.
Yeah. And by the way, the planetarium that you're occasionally seeing is a piece of software called Stellarium.
Yes.
And it's free, right?
Yes, it's free on the desktop version. The phone version is not that great, and it's on. But yeah, it even allows telescope control.
Mm-hmm. Yeah, okay, well, Woody made a point.
Yeah.
Excuse me. Kind of cold up
How do
here.
you deal with field rotation? We're taking very short exposures, so that isn't really a problem right now. And we're not trying to, stack them or try to stack a bunch of them over the time. So for right now, how we have it set up, the field rotation doesn't really matter.
Yeah, field rotation.
What is the maximum exposure can make without equatorial mount? I don't know. I haven't tried. It also will kind of depend on your pixel size of your camera. Right now, we're binning to get maximum SNR, so it really depends on what you're trying to get out of the image, like how much tolerance you have for trailed stars. But there's a lot of people who take 1 second exposures with these type of go-to DOBs and stack a bunch of them at a really high gain, so that you can get a really good image. And the advantage of doing those short exposures is that you can beat seeing you can beat the atmospheric seeing and get maximum resolution. So, yeah.
Okay, and Woody also made the point that what we're looking at is an image of where they were 105 million years ago.
Yeah.
Because it took the light 105 million years to get to the telescope where we are.
If we think about it in real time, like what it's doing like at this moment, then it's probably already much different and probably more collided, more intertwined. Yeah. We're just seeing a snapshot from that time.
Yeah. Well, what's nice is this is a time machine.
Yeah.
we can't go forward, but we can go backward.
Yeah.
Yeah.
All right.
Okay. So
ready?
I think we're going to head on to another galaxy that some of you are probably familiar with. It's called the Whirlpool Galaxy, M51. If any of you ever watched that series Big Bang Theory, they always had a picture in their apartment on the wall of M51 because it's a pretty captivating image of that galaxy, or you might want to say galaxies.
Long gone from here now.
Yeah.
Haha.
Okay, you can see we're moving pretty fast through space.
Indeed.
Yeah.
Ah, there we are.
Okay. Oop. There we were.
Decided to.
Uh-oh.
It's doing some time jumps. There we are.
Okay. Wow, centered. Look at that. Okay.
Good job.
Yeah.
All right, let's get a better image of this. 7.5.
Okay. Depends on field of view and position in the sky.
Yeah.
Yeah. Well, those are technical things people can read. Yeah, I can do 4 with
Yeah, because if you're at
he
really,
uses a hyperstar with an 11-inch scope.
if you're at a really high altitude, it's the sky when you're going from west to east, the sky swings around 180 degrees, so it becomes really fast. But with how we're doing it right now, we don't really care about that too much. Plus, what we're viewing objects are kind of setting, so.
Just like warp speed on Star Trek. You got it, Fred.
All right, let's see this. That's much better. Oh yeah, that's a good galaxy. Yeah.
Yeah, we got the Enterprise cheap because it's old technology.
Oh, there we are.
Okay, you want to talk about that a little?
Yeah, so this is this is a spiral galaxy that is interacting with the elliptical galaxy over here, and so what we've got is if we take let's take a longer exposure so we can get it. What you can see on this object is there's a lot of tidal streams from the interaction. So let's wait for the exposure. We should be able to see that very clearly.
So that means stars and dust are being pulled out of that galaxy and captured by the gravity of the big one.
They're just creating a really big mess of stars and dust as they collide. So all right, let's stretch that.
Yeah, anybody got questions about that? Which constellation?
It's also in Ursa Major.
It's in Ursa. No, it's in. It's in.
Is it?
No, it's
is
not.
it? It's near it.
It's near it.
Is it Canes Venetati?
Canis Venetici, right?
Ah.
Yeah.
Let's look at the
hunting dogs. It's in the hunting dogs. Canis
Venetici.
Venetici.
It's just outside the border.
Yeah, there you go. Fred chimed in on that. No, he didn't spell it right, but we got it. Okay. Thank you, Fred.
Right.
Okay.
All right. Yeah.
Yeah. So that one's very popular, very photographed, and for obvious reasons. It's just interesting.
Yeah.
You can you get a sense of the motion and the forces at work.
There's a lot of this galaxy's been studying virtually every wavelength: radio, infrared, ultraviolet, and they can see they can see this happening, and they can see the actual how the gas is moving in and zoom in. All right, we'll zoom in.
To zoom in, okay.
Yes.
Yeah, okay.
The stream is at a reduced.
How long was that exposure?
That's 30 seconds.
30 seconds, okay.
It's pretty good for 30 seconds. Yeah.
Well, we got 12 inches of telescope and a pretty good camera.
Yeah.
Yeah. And the colors kind of showing too.
Yeah.
The blue in there and What are the blue areas?
The blue areas are younger stars. So they're younger stars. They're earlier in their lifetime, and they're also a lot of them have more metals from the previous generations of stars that released the metals they fused in their cores out into space. And then the orange ones are more older stars. And you tend to see the older stars more near the core of the galaxy. So.
And isn't there a supernova? Wasn't there a supernova found?
There's always supernovae found in these galaxies. Yeah. A lot of them quite frequently have multiple. Yeah.
Okay, so Fred, are we zoomed in enough for you? You can reach out.
Grab the galaxy.
Touch the sky.
Grab the galaxy into your palms. Let's keep stretching it. There we are. Yeah. You can see that. If you look good, here, you can see the tidal stream here, along here. Let me turn up the gain. Maybe we can see the tidal streams better. Passable. Okay, do you want more zoom? Let's increase that.
Okay.
It's 250%.
This is a 30-second exposure, right? Okay, pretty good. Wow.
Okay, that's a little overexposed.
Yeah, okay.
Yeah, but you can start to see the tidal stream over here. a little bit over here. Yeah.
Yeah. Okay. All right. So now we're going to the cocoon. Pretty.
Yeah.
Okay. Okay, we're going on to another. Oh, Lynn wants to know, how big is the galaxy? Well, we'll have to consult Stellarium, or do you know?
Yeah.
How big is it across?
How large in arc seconds or in light years?
Well, imagine light years. Yeah.
Well, let's consult.
We could compare it with the Milky Way.
Yeah, it's around 4 arc minutes across.
Okay.
Yeah, 4 arc seconds. It's 4 arc minutes across.
Okay.
Along that axis.
That's the apparent size.
Yeah, and then it's 105. It's also 100. No, wait. I'm looking at the wrong one. Oh, jeez.
Yeah, you're in the Siamese Twins. Whoops.
Yeah. Okay. No, this one's. Yeah, it's still 4 arc minutes across. Still.
Okay.
But this one's. Yeah, the distance. It doesn't tell the distance here, but.
But how? What's the diameter?
In light years?
Yeah. Does it
it's
say?
It's probably a couple 100,000.
Couple hundred. So it's bigger than the Milky Way, maybe.
Yeah.
It's
well, there's technically 2 galaxies in here.
Right. That's true.
Yeah.
And could you get that with binoculars?
In dark enough skies, yeah, it's possible. There's a lot of
galaxies. Pretty small, but it'd be a little dot.
It'll be a little fuzz.
Yeah, fuzzy spot. Well, I'm getting a moth in my hair. Okay. All right. Okay, shall we go on to the Cocoon Galaxy?
All right. Okay, let me turn the exposures down so we can see the flyby better.
Okay, Kathy, welcome from San Diego. Good to hear from you.
All right, there we go. Time to go.
Okay, we're moving on to the Cocoon Galaxy. Now, I didn't even know there was a Cocoon Galaxy. There's a Cocoon Nebula. But
what's the NGC designation?
It's 4490.
40. Okay. 4490.
Yeah.
Okay, we're off.
Okay, here, tighten the seat belts again.
Here we go. Okay, here we go. Soon. There we are.
Right.
Landed perfectly.
Mm-hmm.
Let's get a 30 second on that. All right. Let's see where it's right here in the end of Cain's Venetachi.
Okay.
Here we are.
This is also in the hunting dogs, Canis Venetici.
Yeah.
And that's a little galaxy.
Yeah, right? That's interacting.
Yeah, these are.
Let's do some zooming in.
Okay, these are 2 galaxies. Yeah, one large one.
Still settling in.
Yeah, I've got a little bit of a double image there.
Well,
oh, wow, there's somebody from Albuquerque might be joining. Okay, Kathy, well, thanks for inviting people. She's gotten 2 friends watching and invited a friend from Albuquerque.
Right, let's get this centered in. It's in Cain's Venetachi. Okay. Might want to turn off the gain a tiny bit.
So we know a few things about those galaxies, distance or? Yeah,
let's look at so that's 33 million light years away.
33, a little closer.
This is actually a spiral galaxy here, but it's really been because due to its interaction, it's really being torn apart. So,
especially the spiral part, I guess.
Yeah, it's not. It's really become but it actually is a spiral galaxy, just like our Milky Way. But it's really being influenced by gravitational forces of the collision. So.
Oh, Betsy Kanak. Wow, hi Betsy. Long time. Good to hear from you.
Yeah.
And
So
Fred made a comment. He said it makes him think it's kind of a side view of the M51 galaxy.
Yeah.
Yeah. Hi. Yeah.
Yeah. Well, actually, by the end of this month, that the comet from before, the Comet C 2017 Pan-STARRS T2, the one we were watching before, that's actually gonna on June 30th.
Oh.
That's gonna go across the galaxy, across both of them actually.
Yeah.
But that's only gonna be visible from Europe. But,
Oh, really? Well, we'll get pictures probably.
Yeah.
Yeah. In other words, the comet will pass in our line of sight right in front of the galaxy.
The comet we were viewing.
Yeah. My seatbelt on. Right, we don't want to lose you, Jeannie. Okay. Yeah. So
Pretty good view.
So these interacting galaxies, these aren't rare.
There's quite a few of them.
Yeah. So that's what happens. Galaxies move through space, and
they interact.
They have close encounters, and
Yeah.
they're never the same afterwards.
Yeah.
Sometimes they get swallowed up and distorted. It causes new stars to form. Okay. Well, shall we move on to the owl?
Yeah.
Okay, we're going to head back into the Milky Way now, because we don't want to get homesick.
Let's get ready to go.
Okay.
So that's going to be, let's put it back.
Oh, Sue. Hi, Sue. Good to hear from you. Sue Huang is here. All right.
Let's get ready to go.
Been too long.
All right.
Okay, so we're going to go to the Owl Nebula now, which is also a Messier object, M97. It's in Ursa Major, and it's actually close to a galaxy in terms of how we see it.
It's close to the Surfboard Galaxy, M108.
Yeah. Do you think we'll see both of them in the?
Oh, we're getting Curiosity Peak Observatory itself in the shot.
Oh no! Really?
Yeah.
Oh, okay.
Yeah.
Light coming out of the. Oh, that's just the reflection or something. Okay. All right. With that fuzzy bluish thing.
Yeah. Let's zoom in on that. Oh god, there's a lot of insects here.
Okay.
Zoom in on that. We're gonna get a much nicer image of it soon.
Hey, Jerry. All right. Happy birthday once again.
Okay. 8 seconds off.
Yeah. So, what's a talk about Planetary Nebula?
Oh, okay. Okay. We'll wait for the dot to settle
They're
down.
certainly pretty.
But what? So these are like a lot of you may have heard of supernovae, and those are the aftermaths of very large mass stars, where they basically their core collapses and then they blow out the outer layers, and you get a very nice supernova remnant, a very nice nebula, and that's what the things like the Crab Nebula are. And but much smaller, lower mass stars, they don't go through that process. Instead, what happens is when they run out of their hydrogen fuel, they go some different state of diffusion before they finally exert their outer layers in a more passive way. So what you get is a really nice object called a Planetary Nebula. And that's what the M97 here is. And at the center, this little blue center star here is called a white dwarf. And so we should be able to get a better view of that very soon. Are we stacking? We are not stacking because currently it's kind of windy, and we also are moving from object to object, so we're not really trying to stack. We're just going to try to take longer exposures. So it should be sufficient enough.
Yeah. So that's like really the end of the star, really. The collapse of the star.
A star like our sun. Our sun, when around 5 billion years, when it nears the end of its life, it's going to go under the same process and turn into a white dwarf and a planetary nebula. So, well,
so
if you can.
So that star at the center is that
that's the white dwarf.
That's the white dwarf that's still out there. I mean, it's still producing light. Yeah. And giving off energy, but it's greatly reduced.
Yeah. Well, if you can look very carefully, it might be a little hard to see, but what we have here is there's actually two shells. It's a double shell Planetary Nebula, which means there's multiple modes of where it's shedding out its outer layers. So you can get triple shell, double shells. Planetary Nebulae come in a lot of different forms. And typically what you see is at the outer edges, you see the hydrogen, you see red, which is from the hydrogen that's emitting. And then at the center, you have a lot of greenish blue teal, which is the oxygen. So that reflects how, in general, near the end of its life, a lot of the hydrogen that's left is not in the core. It is in the outer layers. And at the center is where you get a lot of the oxygen. So that's what you see in a lot of Planetary Nebula, including the Owl, and in, let's say, the Helix Nebula, which is one of the more famous Hubble photographs. And you also have the Ring Nebula, which is also really famous.
We're gonna take a look at.
Yeah.
Yeah. In fact, we got a couple more Planetary Nebula to look at.
Yeah.
So you can see those two dark spots. Yeah.
That's what the Owl. So the guy who really gave it the name, Owl. It was an English astronomer called Lord Rosse, and he did a lot of different drawings of deep sky objects, including what we have is the owl, the crab, and he basically gave those nebulae their name. Whether they're apt names, well, we'll let people decide.
Hey, Jerry said something about water ice in the shell. Maybe, Jerry, you want to chat about that?
Yeah, so in Planetary Nebula, you get a lot of really different substances that you can be formed. Like, for example, another interesting one is called helium hydride. That was discovered in a Planetary Nebula, and it's actually a very unusual because helium is usually known as an inert element that doesn't really react with anything, a noble gas. But what you have is hydrogen ions. So what you get in space, you get really crazy compounds.
Things that don't happen on Earth.
Yeah.
You
wouldn't get
no
that.
helium hydride on Earth. Yeah. Wow, I've never even heard of helium hydride. So,
And it comes.
It's a stable.
I mean, that's what we
molecule?
detected it.
Yeah.
On Earth, definitely not stable. But you can get 4 hydrogen ions to a helium. There's a lot of different craziness you can get with these objects.
Jeannie says 23 million light years away.
Yeah. Let's.
Is that how? Really? That would be outside the Milky Way.
Let's see where it's pointing. M97. Okay. To zoom in more. Yeah, there's the owl. And it's 2025 light years away.
Oh, okay.
And it's 3 arc minutes across.
Knock a couple of zeros off.
Yeah.
Okay. Yeah, beautiful object. That Planetary Nebula are fascinating because they're just like jewels.
Yeah. And it really reflects what you can see on what our sun could potentially be. Yeah. So, yeah, we're seeing this 2,000 years ago, a snapshot. And it's slowly expanding. So, give it a couple of years, give it a couple hundred years, you could see some visible expansion, depending on the rate. Yeah.
Didn't you do a project about measuring?
Yeah, I did a project on measuring the expansion of Planetary Nebulae, like comparing images from 100 years ago taken with the photographic plates and with current images with pretty large telescopes now, and then using that to calculate the expansion rate in general. Because that tells you a lot of things about it. Yeah, the Cocoon Galaxy is 225 million light years away.
Okay, right. Thank you, Jeannie.
Is the M97 Milky Way? Well, yes. Planetary Nebulae the Planetary Nebulae we see are in the Milky Way. Technically, we have been able to spot some Planetary Nebulae in, say, Andromeda.
Really?
But in general, the ones that we amateurs can observe, those are going to be in the Milky Way.
Yeah, right. Okay, so we're going to head over to M57.
Yeah. Okay.
Yeah, all these planetary nebulae are in the Milky Way. We wouldn't be able to see them. I mean, we can actually see them fairly well because they are close enough.
Let's set up SharpCap.
That's going to stack images?
No, I'm gonna do shorter exposure so we can see it better.
Oh, okay.
Turn up gain though.
All right, we're getting to...
Let's zoom better. Auto. Aha, there it is.
Okay, wow, what's that?
Geez, I wonder. This is a pretty bright object
Now
too.
that's M57. Anyone might want to guess. Some of you obviously know what it is, but it's the ring.
Yeah, let's zoom in. Maybe I can lower the binning.
Oh, it's getting a little more detail, a little smoother.
All right, let's turn up the
Look,
gain.
your tanks welcoming. What would it be like to travel through it in a... Oh, Jerry was contemplating traveling through the Owl Nebula in a spaceship.
Yeah, SharpCap does stack in real time. Yeah.
Okay.
Okay. Let me reset the stretch again. That's a good image. For sure. Let's turn down the gain a bit. Yeah.
Oh, okay.
We might
Now we're seeing the red and the
If the Dob settles down better, then we're going to see the central star. Yeah, you can kind of see it now.
Yeah, there's the central star. That's the
That's
star
the white dwarf.
that blew out the shell of gas. Yeah.
And let me turn up the blue a bit. Yeah, the Dob really needs to settle down.
Well,
I think it's a bit windy.
Yeah, a little bit. Not too bad.
Windows
better than last night.
Stacking is basically taking multiple images of the same object to average out the pixels, so you can get a much cleaner, much more higher signal to noise ratio image. That's what astrophotographers do, and that's how they can take 20 hours of integration of data on, say, any faint object without having to expose for 20 hours.
Yeah, and it improves the image quality greatly.
Yeah.
Yeah. So, because these are objects that are faint, and if we take really long exposures, then an airplane flies through or something, it's ruined, and also it's harder to keep. The telescope has to stay steady. Yeah.
There we go. Yeah, this wind is being a little atrocious.
So we are stacking?
No, we're not stacking.
Oh, okay.
We're just viewing it live.
Yeah.
The wind is too atrocious to do much.
There's a little breeze up here, because to stack the images can't be moving around. That's one of our enemies.
I'm not sure if SharpCap does allow you to do image alignment in real time. But yeah, the wind is being a little non-cooperative, but it's okay. We can get good images.
Yeah, we're managing.
Yeah, actually,
a couple of nights ago, this would have been impossible.
Let me see how bad the wind is. If we can take a look.
Well, it can't be good, that's for sure.
Definitely, yeah. Oh yeah, the wind is just going on a rampage.
Yeah.
Yeah, my setup's doing 2.9 arc-second guiding.
Really? Okay.
Jeez. Well,
yeah.
I guess that's how bad the wind is.
Yeah. Well,
Chandrasekhar limit. Yes.
Okay.
Yeah, so white dwarfs tend to have a mass limit due to their Helios close to Arcturus 1790. Okay. Well, so the Chandrasekhar limit is the mass limit of white dwarfs, and that's because when you have atoms with electrons, you can only have 2 electrons at a time with different spins up and down. So if you compress the atoms down, like what happens when a white dwarf does core collapse, what can happen is that because the pressure is getting too high, it can over the because the electrons cannot be in the same orbital. What can happen is we can reach that limit, and what happens, like if you have a white dwarf and another star, and that white dwarf is taking material, it can go over that mass limit where the electrons get too compressed, and what happens is you get a type of supernova called a type 1A supernova. And that's one of the common supernovae we see in galaxies, and we can actually use that as a standard candle because it has a certain luminosity because we know what the exact mass is and what the trigger is. We can use that to extrapolate how far away galaxies are. So if we see a certain galaxy where a white dwarf has accreted material and gone over that limit of 1.4 times the mass of the sun, you have a supernova, and you can use that to measure how far away it is. Now there is some leeway, there's some error with doing that calculation, but it's one of the ways we know how far away galaxies are.
So it's another way to measure different from the like instead of the Cepheid
it's
variable.
always good to have it's always good to have multiple ways to measure something so you can get an accurate picture of how far away it is. Okay.
Yeah, Jeannie likes the color. Yeah, I do too. Yeah, the Ring Nebula is beautiful. It's got the green and red. Okay, yeah. All right, so...
Do you want to move on?
Yeah, we're going to move on to M27.
All right.
I believe it's almost 10 o'clock.
I think, Jerry was asking about a Haumea. It's close to...
Yeah.
What is it close to?
Arcturus?
Yeah. 17.7 mag. It might be a bit different.
That is an example of...
That's one of the dwarf planets.
Oh, Lynn wanted to know what's the red something on the outside of the image.
That is the hydrogen. That is the hydrogen in the Planetary Nebula. That's hydrogen alpha. So.
Yeah. Red is the signature color of hydrogen.
Okay, so we're actually getting limit to our object list, so we might be able to catch Haumea.
Oh, Haumea, a dwarf planet.
Yeah.
Oh, really? So that's a suggestion of something to look at. Okay.
Yeah, we can try it.
Yeah. Okay. All right, Jerry. We'll.
There we are.
We'll see if we can. Wow. Oh, there's okay.
M27.
Yeah. Wow, it's looking big there on the screen. Okay, another planetary nebula. Very different from the ring.
If the wind stopped being a little.
Yeah.
Be more cooperative.
Yeah, like hit the pause button for the wind. Well,
do better.
Okay, well, we're seeing... Oh, there you go, yeah. Okay. That's also called the Apple Core Nebula? Or
yeah, I think it's a more apt name.
Yeah.
And you can see the same pattern of the hydrogen alpha being on the outside, and you have the oxygen in the inside. So there are some hydrogen streamers within the body of the Planetary Nebula, but that's hard to catch when you have the wind. But let's try to go... I think we can try a little longer exposure. We'll catch one that's good.
Okay, well now, Lynn, now you know why we get hooked on astrophotography. Because these things are
unnatural obsession.
Yeah.
Jesus, wind.
This is the light show of the 21st century.
Yeah. Yeah.
The psychedelics of the cosmos.
Let's try it. We might try it. Let's try that. Let's try stack.
Shorter integration times and stack. Okay.
Well, it might be difficult.
2030 light years away.
Ah, no.
Thank you.
Don't tell me about this. And this might be a bit. It's definitely.
Because that fixes windy nights. Okay. 8,000 years old.
Yeah, we might have to try this. Yeah. Let's let it go.
Break out your wallet? Oh, really? How big is that?
Break out your wallet?
Uh-oh.
I don't... This is... I need to move this down.
Is that the white dwarf in the center?
Now we're stacking.
Okay, Lynn wants to know if that's the white dwarf in the center.
Correct. Yes.
All right, Lynn. Damn, you're becoming an astronomer. You better watch out.
Better watch out. You're gonna have to spend a lot of money Be careful. It's coming towards
Lynn
you.
wants to know how big is that?
In terms of arc minutes?
Yeah. Well, I think.
Let's try.
How large across?
In light years, I'm pretty sure it's like 20. Pretty sure it's like a 30 light years across.
About 30 light years across. Okay, Jerry says add the stacking feature.
Yeah, it is stacking.
Oh, it is stacking. Okay.
I'm pretty. Yeah, it is. It's stacked 29 frames so far.
Okay. Well, we're certainly getting more. Oh, it's.
I need to find M27 here. There it is. Scope's pointed there.
And that's in what's the constellation? Aquila.
It's in Vulpecula.
Oh, Vulpecula. Okay.
Yeah.
What does Vulpecula mean?
It's a fox.
A fox. Okay.
This is 8 arc minutes in diameter.
Okay.
Let me see if we got that.
Balance the channels on the camera.
Oh yeah. Well, I might. Let's see. Okay. Yeah. Okay. Let's got this.
It's kind of like a sphere, almost like a glass sphere, with. And that's expanding still, I imagine.
Yep. You can now see the streamers. Oh wait, I did something. Let's get it back.
Oh, we're getting. That's a pretty...
You can see the streamers, the hydrogen streamers.
Oh, that's pretty good.
It's being a little touchy.
Yeah.
Okay, that's okay. This is a little better. But yeah, we're reaching the limit too. Okay, yeah. So.
Okay, yeah. So
let me see if we got the exoplanet. We
Oh.
did.
Huh?
It's there. This star over here.
Really?
That has an exoplanet.
Oh, really?
It's called HD 189733, and it's got a pretty big exoplanet. It's around I think it's like 1.7 times the mass of Jupiter. I have to check, but it's one of the easiest exoplanets for like amateurs to do photometry on and see. You can do it even with a camera lens. But yeah, it's right next to the dumbbell.
So the planet passes right across.
Yeah, so you got the planet transiting the star, and you can see that. It's right near one of the more famous objects in the night sky. Yeah.
Okay. Well, gee, that was unexpected visit. Okay.
Yeah.
All right. Yeah. Well, anyway, this is an object you can see with a relatively small telescope too.
Yeah.
You know, in fact, most of the things we've looked at, you don't need a really big telescope to see them.
JWST. Well, let that launch first.
Oh, James Webb.
Yeah, we need that to launch first. Then
Okay.
we can get some good news.
Yeah, we're going to get some time on that. We're going to...
2021?
Okay.
Yeah.
Really,
Yeah.
there's
Let me get the stretch
the
a little bit
bulges
more.
Upper left and
He's
lower right.
talking about the wings. Like,
Yeah.
you got like wings, mostly oxygen. If we took a really long intubation and say narrowband with the more sophisticated setup, you could see there's more flares across. There's more
Beyond.
layers across the Planetary Nebula from the initial pulsations. But yeah. Okay.
Okay, well, we're going to go on from here to M13.
Let's do that.
Okay, we're going to... Yeah,
Yeah, we'll reset
there we
this.
go. Kind of
Stop with this. I don't want to pay with this money. Okay, there we are. Yeah, that's too much. Let's go.
Okay.
All right, what's next?
Okay, we're moving on to the Great Globular Cluster in Hercules.
Yeah, M13. Let's go.
M13, right. It's about 300,000 stars. And they're all the same age, which I think most globular clusters.
Just very high up.
And this is also an object that with a moderate or small
You can even do it with binoculars.
Mm-hmm. But
Hey!
the larger the scope, the more you see the individual
It
stars.
landed on the edge.
Hmm?
You gotta fix that.
What's that?
It landed on the edge of the scope of the field of view.
Oh, yeah.
Let's bring it back.
Okay. Well, it's in the neighborhood anyway. I think you gotta go the other way, I think.
Yeah. It's taking
There
a
we
little
go.
time to expose. Oh, you already see the propeller. It's nice.
Oh, yeah. Jerry mentioned M92. We could look at that,
Yeah,
too.
that's the next on the list.
Yeah. Well, actually,
It's
not,
a more
but-
concentrated globular cluster.
Yeah.
It has a pretty
It
big...
was on our list, and now it's back.
Yeah. We didn't think we were able to get through these many objects in the night. Setup is working too well.
Mm-hmm.
Alright, I think that's enough. I don't need it to be extremely centered. Yeah, we're gonna overexpose.
Well, Ernie wants to know when we can see Omega Centauri.
Well,
10 million.
we're gonna have to go to... It's pretty... Even if it's
Well, we could see
pretty
it
low.
from here, but it's
Pretty
low.
low.
Yeah.
Better to get it from the southern hemisphere. I don't know
Yeah.
if it's in season, though. Oh, let's see.
Okay.
This is... Let's get this centered. Okay, let's zoom in. It's a little too zoomed in, I guess. 125%. Let's do this.
Oh, we have a friend from Debbie from New Mexico. Wow, Albuquerque. Cool, Debbie. Good to have you on board.
Yeah, the Omega Centauri is really spectacular. Even
Yeah.
if when it's like 10 degrees above.
Yeah, and with binoculars even, it's really something.
I think it's... Yeah,
And if your southern horizon is pretty
very clear.
you can catch it. Yeah.
I might clear this again. Clear. There we are. That's going to be much better.
Okay.
Wanna
Kind of reminds me of a spider.
We can let's see if we can get a nice view of the propeller.
Mm-hmm.
Yeah, let's. I don't know if people can notice, but there's a dust lane in the middle.
Mm-hmm.
There's a dust lane in the middle over here. It's like a three-way propeller, and it's one of the biggest. It's one of the more striking features on M13 when you look at it, because. How bad is the wind?
Doesn't feel that bad.
Well, we're down
Yeah,
here.
Yeah.
It's the top of the
Right.
telescope.
Yeah, the telescope is catching.
Yeah, it's not that bad now. It's pretty. It's okay. Yeah, it's decent enough. We're good.
Oh, that's interesting. So the stars, Jerry's pointing out that the stars actually orbit the galactic core.
Yeah,
Okay.
we have also, the galactic halo is where a lot of the globular clusters reside,
Mm-hmm.
and we can also see the globular clusters in Andromeda. If you have a very large telescope or you're doing imaging, you can actually spot one of them. I think one of the brightest one is called Mayal 1.
Yeah.
Is it 1 or 7? I don't know.
So globular clusters are probably
Andromeda G1.
something found
Yeah,
in galaxies.
yeah. There's an
Yeah.
entire survey
Yeah,
of lots of globular clusters in Andromeda,
Mm-hmm.
and
But the ones we look at, they're all in the periphery of the Milky Way. Though.
yeah, because the globular clusters usually reside there. But yeah, globular clusters tend to have older stars compared to open clusters. They tend to be tend to have more stars that are shifted more towards the orange. So this might be a good time to talk about what colors and stars mean. So
Mm-hmm.
when you look at a star, usually if you look at the color, you can tell what temperature it's at. Because the more blue it is, the hotter it is, and the more red it is, the more cooler it is. So if you take like an iron and you start to heat it up, starts to glow red. So it goes from the infrared to the glow red. Then if you keep heating it and heating it, it can glow wider and wider. And if you theoretically get it very, very hot, you can get it to glow blue. And that's stars that are really hot, they glow blue.
Like Vega, right? Vega.
So that's what you see in in a lot of clusters. You can see blue and orange stars in different colors. Those are all indicative of temperature.
So we
population 1 and population 2. Yes.
Yeah.
Yeah. So
we got Tapan Patel. Welcome.
So there's two different populations of star depending on how old they are. We usually tell them by their metallicity, like how much concentration of metals there are, because the younger stars get their metals from older stars that are preceding generations of stars that have taken out their metals from, fused it in their inner core, and they've spread it across.
Going supernova,
or it can be one of the more lower mass stars, but that's just generally how stars get seeded and how interstellar disks get seeded with different elements and can create planets and those sorts of things. Some globular, like Omega Centauri, for example, it's speculated to perhaps be the remnant core of a dwarf galaxy that the Milky Way took in, but there's still a lot of work to be done in that, but usually when we plot what their Hertzsprung-Russell diagram is, or the plot of temperature versus luminosity, and we look at the pattern, we can date the globular cluster. So usually we can see them to be around like 10 billion stars.
They're old, right?
10 billion years old. Like they formed a really long time ago. They can be captured among galaxies, yes.
Okay, Woody says we've stolen several over the years. Yeah. Clusters can
How many
move
stars?
between galaxies.
I believe it's 300,000 estimated.
Stars in the
M13.
Yeah, in M13.
You can see purple haze at bottom.
It's the biggest one. We can see it in the northern hemisphere. Well, we can get a glimpse of Omega Centauri is bigger, but it's generally considered something you can see in the southern hemisphere. But we're far enough south that it kind of bobs along the southern horizon for a little while, and you can see it. We have been able to image it from Curiosity Peak. Of course, going through a lot of atmosphere, so it's don't get great images of it.
Yeah. Okay, so hopefully everyone noted the propeller. Dust line. All right. Are you ready?
Yeah. Jeannie says she can see purple haze at top and bottom.
Well, I guess that's the color balance and the amp glow and all of that.
Well, it's not Jimi Hendrix out there doing purple haze. Okay.
I'm too young for that reference.
Okay. You've heard of it.
I've heard.
Of him. Yeah.
Yeah.
Yeah. Okay. M92 request.
Yeah, that's our next one.
Okay. We're going. Okay.
Oh boy, there's a lot of spiders.
Yeah.
Jeez. There's one right crawling across the hand controller.
Fred, keep the social distance there now.
Okay, I killed one. Getting too close for comfort. Okay, let's...
Yeah, Ernie says it's in May when we can see it. Okay.
Yeah, okay. We're like 1 month out. Let's go. Should get it soon. Let me clear pause. Aha! Again, it's in the corner.
Yeah, okay, well, predictable.
Let's get it out of the corner.
Okay.
Go.
Okay, we're gonna zoom into the center here.
Yep. The main thing to note here is to compare it to how M13 was.
Mm-hmm.
I think this is the same gain and
It's much more compacted.
This is the same gain and exposure, but the center is way more compact.
Mm-hmm.
So there's a classification schema of globular clusters. I believe this is type, I believe it's like type 10 or 13. But that generally tells how concentrated the globular clusters are. I'm not really familiar with what each classification of the globular clusters are, but let's just zoom in.
Okay.
Life stack. Okay, that's a bit too zoomed in. That's better. Yeah, a little less. Okay, let's stack.
Well, the center looks very dense,
It is. Okay, let's fix this. Right. Yeah.
27,000 light years away.
Okay. Yeah. Yeah, so M92, it's a more concentrated globular cluster than M13. Makes a really nice visual target too.
Lynn wants to know how big is it? How many stars?
I am not sure how many stars it has.
Well, Jerry
I
said
know
something about
M92. I know what
300,000.
M13 was.
Yeah,
Well, yeah, 300,000 stars I think is for...
M13.
Yeah, I'm not sure. But yeah.
Well, is it there? Did they tell you?
8,200 kiloparsecs, so that's 26,000 light years away. It's definitely in the... Yeah. It's pretty bright in the center. Look, even Stellarium had to do HDR.
Huh. Yeah.
Yeah, this is... Armchair astronomer, yeah.
Yeah.
Coronavirus
I feel like
time.
a Dirondack chair astronomer.
Yeah.
Huh.
Okay.
Okay.
Okay,
we're gonna do the iris, right?
do you want to do the Haumea?
Haumea? Yeah, okay, if you think we can get it, yeah.
It's a big slew.
Well,
Wait,
or
let me
is
see
iris near it?
We'll have to get the... I think he had the coordinates. It'll be a difficult one to spot. We could go to the... Iris is close. We can do the iris first, and then we can go to Haumea.
Okay.
That'll be our closing
Yeah.
object. Yeah.
Okay.
Okay. More pretty picture object. Wow. There it is.
Okay. Oh, the iris, yeah.
Yep. Let's stack.
Okay. Okay, it's starting to show up a little more.
No, we have not done that for this job because we didn't really anticipate we would try to do anything much faint. I mean, my 8-inch note was able to get, I think, magnitude 18 with the ASI 290 stacking.
Have you calculated mag depth on this image?
No, this is the first time the 294 is going on the 12-inch Dob. Well, the second time. We did it yesterday to test it out. Well, no, yesterday was first flight, technically, with the 294.
Yeah.
I've had the Dob for a while, but we had the 294 was really recent.
Yeah, this is the debut of the camera. Okay, so that's a reflection nebula?
Yeah.
Which is bluish.
Okay, let's zoom out. It's a more extended object. You might have to take longer exposures, or I think the gain is pretty high already.
Okay, we're starting to see more of it.
Yep. Let me.
Yeah, notice how it looks small, but there's really a lot more as we get more imaging time.
Let's not get raining noise. That'd be suck. Oh yeah, you can start to see the dark nebulae now. Yeah, here we go. To zoom out even more. There we go. It's showing up.
Yeah, there's actually brown in there, and
here we go.
besides the blue.
It's getting better. Try increasing the.
Oh yeah.
Oh, that's too far. Okay. Keep going. You can stack.
639 frames.
Yep.
Wow.
No, that is how much we've taken over since the entire time.
Oh, okay.
Yeah, we're only taking. This is 44 images. 2 minutes and 11 seconds total.
44 images. Okay. Yeah. So, Lynn, this is an example of stacking. We're actually doing some stacking now to enhance the image.
Yeah. Really needed for the iris.
Black body radiation.
Yeah, that's the type of radiation given from a theoretical. If you had a theoretical black body, it would have a perfect black body spectrum. That's what we used to model the spectrum of stars.
Okay.
Yeah. All right, we're coming into an end in 7 minutes.
Okay.
Maybe we'll have time to go to Hamiya.
Lynn is signing off. Good night, Lynn. Thank you for coming.
The dark brown regions are baryonic matter.
Metal is like, dark, or baryonic matter.
Yeah.
The dark brown regions. Oh, okay.
Is it? I think it's stacked a bit.
Okay.
Let's push this. And we might be exceeding the capacity of 3-second exposures at 470 gain. We're hitting the.
I think we got the purple haze again. Yeah.
Purple haze.
Nice. Or the riders of the purple sage, maybe.
Let's tack these.
Light years of soot, matter from the star's shell, Earth-like material. That's from Jerry. Thank you. Floating mud. Fred's interpretation.
Let it stack.
Wow, so a lot of planets could form out of that. There was something, a star that pulled them. Well, there is a star there at the center, isn't it?
Yeah. It's part of what it's a reflection nebula. So it's part of what illuminates the blue part, the reflection nebula. Yeah, these kind of molecular clouds they provide.
Okay, so it does provide material for solar system formation.
Gonna let it stack.
A lot of material out there.
Three, 2, 1, 0.
Okay.
Yeah, might be. I guess the rest of the nebula is just across the field of view. Yeah. But yeah, we got a pretty good picture of.
But you can see how it blocks the stars out there. That absence of stars there is because of the dark nebula.
Yeah, it's pointing here. It's very low right now, the iris. Maybe we can go to the ghost. It's right near it.
Yeah. Okay, one more.
One last parting thing, then.
Okay.
I don't know if Jerry still wants to try to get Hamiya.
Well, yeah, maybe.
What's Yeah.
Huh? Huh?
See, so we have the ghost. The ghost is right next, adjacent to.
The ghost of what?
So
Just the
it's
ghost?
just called the Ghost Nebula.
Oh, okay.
Not sure what the. Let me
The designation.
let me do some research.
Oh, it's Jerry. Hello. Jerry. A technique for what? Uh-huh. That's for the Haumea?
There'll be one star in the mix that will actually start to draw a line. And that won't be a star, that'll be Haumea.
Okay. Well, we can do that tonight, or?
Yeah.
No, I don't know.
Yeah.
Take me off speaker.
Huh? Huh?
Take me off speaker.
Oh, okay.
Yeah.
Okay.
Yeah.
Yeah. Got a lazy ear, you know. Yeah, you are.
Okay. All right. Thanks. We'll just close off with this view of Iris, the iris.
Okay. Mm-hmm. Mm-hmm. But it can show up. Well, okay. Yeah. Yeah, well, they're... Uh-huh. Uh-huh. Yeah, right. Uh-huh, the dwarf planet. Okay.
Okay.
Yeah.
That's better.
Uh-huh. Yeah, well, it's about 10:30, so it's kind of wrap-up time. But, oh, we got the Crescent Nebula?
Yep, it's Crescent. We're gonna end with this.
Okay, well, thanks for joining in. Okay, and thanks for your providing some good information too. Yeah, yeah. All right. Okay. Yeah. So are you going to stay up tonight? Okay. Well, maybe we can talk later. I don't know. I may not be staying up real late. But yeah. Or I'll call you in the morning. Okay. Either. Okay. All right, man. Take care, and again, happy birthday. Bye.
All right. So we're gonna close off with the Crescent.
Okay.
Yep.
Yeah, Crescent Nebula.
That's Wolf-Rayet star that's shutting off its outer layers very slowly.
Mm-hmm.
Yeah.
Is that the star right there?
Yep, that's the star.
Uh-huh.
I think it's WR 137.
Okay. Wolf-Rayet star.
Yep.
Yeah. Don't they rotate?
They rotate really fast. Yeah,
Yeah.
they're very hot.
Yeah. All right. Well, thank you, everybody. This has been fun for us, I think. And
Yeah.
everybody stay safe. Keep looking up, and we'll be doing this again, I imagine.
Yeah.
This has gone a little smoother than the last one.
Definitely. Yeah. But
Yeah.
the equipment's more cooperative.
Yeah.
Wind has died down a bit. Yeah.
Okay. And I just want to thank Vivek. This was his brainchild, really, and I'm assisting, but You know, we got it together. So, any suggestions or thoughts, you know, shoot them our way, okay?
All
Take
right.
care.
Okay. Good night.
Are you sure you want to end?